Hello everyone, I'm very glad to be here. I'm not an economist and it's not an economics talk. I have a physics background. I'm now a professor of sociology, and let's see what we might be able to learn from that experience. Overall, I call myself a complexity scientist and like to start with a number of examples, hopefully to inspire some discussion. So in economics, the concept of equilibrium is very important. Of course, not everything is thought to be in equilibrium, but it's dominating. And much of it has been inspired, if I'm well informed, by thermodynamics. Now, we know that thermodynamics is a very important concept of physics, but in the meantime, many new areas have developed, including complexity theory, non-equilibrium thermodynamics, dynamical systems, and so on. The question is, what implications might that have for economics? Can we learn something from that? And I'd like to start off with an example that somehow demonstrates the principle of Adam Smith's invisible hand. I show it for a non-economic example where pedestrians are interacting with each other, and in a very magic way almost, people are self-organizing in these lanes of uniform walking direction. So it's a coordination of their behavior, and they're usually not aware of that. It happens automatically, so it's really like magic. And one could consider that as an instantiation of Adam Smith's invisible hand. However, it turns out that this invisible hand doesn't always work. And so the question is, would it always work in economics? When the density goes up, and by this the coupling between the pedestrians is getting stronger, that means the interaction is stronger, then things can get terribly out of control, as illustrated by crowd disasters actually. I don't want to show this movie because it's really shocking, but this phenomenon is based on instabilities in the crowds. And even hundreds of policemen won't be able to control the situation anymore once we are under these kind of high-density conditions. I'm showing you another example that you must be familiar with. An experiment where drivers were asked to drive continuously, but of course avoid accidents from happening. Each of them is well skilled. Each of them is trying hard to avoid a traffic jam from forming. Everyone wants to go at high speed. But what happens is everyone ends up being stopped. So things get out of control. And the question is why? If you would ask drivers why that happened, they would say, hey, there was a stupid driver in front of me who didn't know how to drive a car. And everyone would say that. However, there is a theory explaining these instabilities. So when the density goes beyond a certain threshold, then basically small variations in the velocity amplify. This successive driver will have to tip a little bit stronger on the brake in order to compensate for delays in adaptation. There is a reaction time. It takes some time to brake. So in order to avoid an accident, you have to brake harder. That creates amplification. And then there is a cascading effect. That means the second next driver has to brake even harder, and so on, until everyone gets stopped. Now there is another interesting effect in traffic. If we were economists, we would say, okay, we should operate the system at maximum capacity, at maximum throughput to make it operate it efficiently. But as you do that, you get to a point of instability. But your system will not stay at that capacity. What happens instead is that there is a capacity drop. And that capacity drop happens just at the time when you need all your capacity. That means the very same freeway won't transport as many vehicles anymore as it did before. And that happens just in the rush hour when you need the capacity. So bad things can happen in complex systems with many non-linearly interacting components. And the question is, why wouldn't these things happen in economic systems? Well, in fact, we know John Sterman's beer game, and here again there is a situation where even well-trained managers, as those well-trained drivers, would not be able to control the system well. So we would find a bullwhip effect, and small variations in demand would add up, they would amplify, and things would get out of control. And so the question is, why wouldn't cycles of booms and recession be of this very same nature? In fact, we came up some time ago with a model of supply networks, a material flow network model, assuming, however, delays in adjustment to change demand. And again, you would find such a stop-and-go kind of motion, but moreover, what you additionally find is that given realistic supply networks, input-output matrices actually, you find non-periodic changes in your economic output, as you actually observe it in reality. So do we need economic shocks? Do we need innovation shocks to explain this irregularity? Maybe not. Maybe you can gain a better understanding. Now also, many people think more liquidity is better, but some people are also skeptical about it because they think as you provide more liquidity, you would drive your market into a situation that would destabilize it, and rather than making targeted investments into real values, you would get into a situation where you start to speculate, basically to make bets on investments, and where you would get instabilities and herding effects and these kind of things, and maybe of arbitrary size almost. So there may be reasons to think about it again. There's also a widespread belief that markets are efficient, in particular financial markets are efficient, but recently we've seen these kinds of phenomena, like flash crashes, where it turns out that after months of investigation, there was no criminal act that caused the problem, where $600 billion evaporated in 20 minutes. Was also no fat finger, that means no human error, there was no machine error. It seems this was an interaction effect of trading algorithms. More than 50% of financial trades are now carried out by computers. And this was not the only instance where we found such a dynamic. So are markets really efficient today? I've done another study actually where we have used Google Trends data, Google search volume data, and compared them actually with markets developments. And the results suggest that it would have been possible to make enormous profits during the time when the financial markets broke down in particular. Why? Because Google somehow manages to see into people's brains. So before people make an investment, they would inform themselves, and Google would be able actually to measure these searches. So in principle, before people invest and the market responds to those investments, Google might be able actually to identify possible plans of people and make trend predictions, which of course would not be reliable, as the weather forecast wouldn't be, but altogether it would possibly allow to make some money. But it also questions this idea that all relevant information is in the price. Using this additional kind of information, however, would maybe allow one to make markets more efficient. Well, let's come back to Adam Smith's principle of the invisible hand. So the free market paradigm is based on this principle, and It's often paraphrased in a way that, by the way, Adam Smith himself didn't paraphrase this way, that selfish behavior optimizes the systemic outcome. So if you just do what is good for you, it would be good for our society. And let's have a look at another system which we can fully control in our computer. That means we simulate urban traffic. And in this case, our agent who tried to optimize a goal function, in this case, minimize travel times. In this case, those optimizing agents, those selfish agents, would be the traffic lights. So if we tell them to minimize travel times, it turns out that we don't get a good systemic outcome. That means altogether, although locally at every single intersection we try to minimize travel time, it turns out that globally for a car that has to go through the system over many intersections, travel times would not be minimized. That is shocking, but there are kind of interactions, effect that avoid that. For example, two cars would be able to cross this intersection at the same time if an accident could happen. So we have this prioritization of one flow direction at a time, and other flow directions have to wait, and then there are network effects, and that somehow creates a very complex and hard to understand system dynamics. It turns out, however, that we can do much better in terms of travel time optimization if you introduce rules where those intersections would not just only care about their own performance, but also stay in contact with the neighboring traffic lights and try to coordinate a little bit with them. It's still a local principle, and it's still a self-organization principle, but now suddenly you get a situation where this local optimization attempts create a systemic optimum. That means, in principle, Adam Smith can be established. But you have to look beyond the selfishness of the individual agent. You need also to create rules of the game that define the interaction with your neighbors. And then things would work out well. So here are actually some data which show that the performance of this optimizing traffic lights is very good as long as the traffic volume is not too big. But you see that this principle fails long before the capacity of the intersection is reached. We have an explosion of travel times actually much before. So we have to combine this principle of selfish optimization with other principles in order to outperform today's traffic light controls, which largely are top-down, while the self-organization approach is bottom-up. What about deciding rationally? The rational agent paradigm is widespread in economics and also in some parts of sociology, but altogether there's no agreement among the behavioral sciences about the theory which would really describe human decisions. There are many different and incompatible theories. And here is just one experiment among many. Ryan Murphy will probably present you many more interesting experiments. This is an ultimatum game where we have varied the power of proposers and responders. Let us just focus on this setting over here where we have a weak responder in a way that a rational responder should always accept the proposal, no matter how bad it is. And we have compared that actually with another theory, fairness theory, where people would try to minimize differences between outcomes of the two players. And so a fairness-oriented responder would reject here, but should accept over here. Now what we find is that although rational choice theory and fairness theory predict that nobody should reject over here, for these kinds of proposals, that means offers, there are quite a substantial number of people who do reject. That means neither theory does explain the experimental data. There's another experiment that has been performed actually with a team of Frank Schweitzer, with Heiko Rauhut and Jan Lorenz. And that one was looking at estimation tasks. People had to estimate a barely known fact. And we have compared different kinds of settings. One where people have made their estimates several times after each other without getting any information about the estimates of others. And again, other settings where people were informed about either the average estimate or all the estimates of the others. And there was no group pressure or something like that. That was people sitting in cubicles, but still getting information about other people's choices was strong enough to create social influence in a way that it created not just a convergence of opinions, but also overconfidence and sometimes bad performance. So it could happen that actually most people came up with estimates which did not anymore include the true answer after a number of iterations, while in the beginning it was within the scope of the answers given. So social influence might undermine people's capability to estimate, find the right solution. That is particularly bad because many decisions are committee decisions and they are surely based on social influence. So we have to think about collective decision-making procedures in order maybe to come up with better outcomes. Then there is representative agent theory, which corresponds maybe mainly to mean field theory in physics. So the idea is that agents can be treated as if acting identically, or the mean behavior is representative. Now, under many conditions, that works well. But we know from physics that there are conditions where strong correlations can be created in the system, or a co-evolutionary dynamics that would basically lead to very different outcomes. So interaction strength changes everything again. And as people are getting more and more connected, and also markets get more and more connected, and companies get more and more connected, we don't have a situation of independent choice anymore, and we expect a completely different kind of dynamics resulting from those interactions. And I'd like to show you a public goods game as an illustration. In that public goods game, we have 4 different strategies. One is to cooperate, one is to defect, that means not to cooperate, that means not to make a contribution to the public good. Then we have moralists, those cooperate, and additionally they punish non-cooperative behaviors in their neighborhood, and that is costly. And we have finally immoralists who are defecting individuals who would nevertheless punish other defectors. These are yellow, and they disappear very quickly. Let's focus on red, which is the non-cooperative one, blue, which is cooperative, and green, which are the moralists. So what happens in a mean field treatment when everybody interacts with everybody else? Well, we know the situation. The cooperators crowd out the moralists because the moralists have an additional cost to pay to punish others. And it means they don't perform as well in terms of payoff as the cooperators. So basically, cooperators disappear and we stay with cooperators and defectors. And we end with the tragedy of the commons. However, if we play the very same game in a spatial setting, where everybody interacts with neighbors and imitates the best performing neighbor, then we find a completely different dynamics. initially, in fact, starting with a well-mixed situation, same fraction for all of the strategies, we see, in fact, that non-cooperative behavior becomes dominant altogether. So if you would extrapolate that into the future, it would mean that defectors would, in the end, dominate the world. But surprisingly, after some time, we see that blue becomes the dominating strategy. And finally, it's the green strategy, the moralists who punish non-cooperative behavior, who win. How can that happen? This is just the opposite outcome from what the mean field theory, the representative agent theory, suggests. Well, it's because spatial interaction promotes segregation over here. That means now the moralists don't have to compete directly with the cooperators. The moralists compete with the defectors, and they have means to punish them and to spread, while the cooperators, when interacting with the defectors, they will be crowded out by the defectors. So that means actually those defectors help the moralists to eliminate the cooperators who don't punish. In other words, that's also solving the second-order free riders dilemma. So we do understand, just by considering spatial interaction, why people start to punish others and why actually cooperative behavior and punishment is spreading. Just opposite to what the mean field theory would predict. Now, we've been often talking today about equilibrium selection, and the way the natural sciences look at this is that they create so-called phase diagrams, which basically say, given certain parameter values, where would your system end up? And there are some of the systems that not only depend on the choice of the parameter values, but also on the choice of the initial conditions. I mean, history matters, and there could be hysteresis effect in these kinds of things. Now, what about moral behavior? We know from experiment that in many prisoner's dilemmas or public goods games, people start with a surprisingly high level of cooperation. So people seem to have other regarding preferences, but finally fail to spread cooperation under certain kinds of institutional settings. Now, we do believe in economics into selfish optimizing behavior because we believe that biological evolution would eliminate everything else. So if there are two individuals, one is selfish and the other one doesn't make use of all the options it has, then for sure the individual who is selfish would have opportunities to generate better payoffs and should spread by biological selection. And that is, I believe, one of the main reasons why we believe in rational choice theory. And even those who think, okay, rational choice theory maybe is not correct, but there are 100 boundedly rational agent theories. So which one is the right one, which one to work with? And here is the proposal how to go about it. So we have simulated agents with biological selection and mutation, as it's assumed in biology. And we've assumed a trait which is called friendliness. That friendliness would spread. However, only if that creates a better reproductive performance. And friendliness, however, on the other hand, is not influencing the payoff directly, nor is there a cultural control of reproduction rates, as in some models. It turns out that nevertheless, even under conditions of a best response rule rather than imitation, where we really expect that cooperation doesn't have a chance in a prisoner's dilemma to spread, that we still can have conditions where other regarding behavior would actually be born and spread. But we also see that in the majority of the parameter space is dominated by rational agent behavior, the homo economicus, selfish behavior as according to classical economics. But there is this other possibility, and the question is, when does it occur? It occurs in our model when there is little intergenerational migration. If intergenerational migration exceeds a certain limit, then this evolution of other regarding behavior cannot happen. But here are experimental data of Ryan Murphy, who will talk after the lunch break, and it shows that in reality there is a broad spectrum of non-selfish behavior. What about networking? We usually believe that networking is good. It allows us to reduce risk. It allows us to generate benefits. And of course, that is true in many contexts. But let's have a look at that particular situation. It's again a prisoner's dilemma. Red is defection, blue is cooperation. We have a situation where people interact in the ring with neighborhood interaction with two neighbors. And we know that neighborhood interactions under certain conditions can create an outbreak of cooperation, as you see it over here. And then what we do next is, in a random way, we add global links between those agents. And so the interconnectivity increases over time. And while that is okay in the beginning, it turns out there seems to be a critical threshold of interconnectedness where suddenly cooperation breaks down. The question is, what implications might that have for our society or for the economy? And maybe the breakdown of financial markets back in 2008 was based on this effect, because over time, as those data from Andy Haldane shown, the banking system became more and more densely connected. So have we created such a hyper-connected situation that destabilized cooperation? It's quite possible. We would have to check that more carefully. And so in the same way, one can show that many interlinkages would increase the size of cascades if you have bankruptcies in the system. And there's nice work by Frank Schweitzer and Stefano Battistone and other co-workers as well. I recommend you to have a look at this video. So I'm finishing with this idea that regulation can fix the imperfection of the economy. And sometimes I think it works, but I don't think it's a concept that would solve all the problems that you could imagine. And why is that? Because there's limits of predictability. Those systems, complex systems, often behave in a chaotic or turbulent way or barely predictable way. And they're also hard to control in certain parameter regimes. They're not responding well to attempts to manipulate those systems, while when you reach a tipping point, suddenly the system behavior would change dramatically. So that is kind of nasty. And also, if you do the intuitive thing in order to drive the system towards a desired state, like over here, then you might end up something very different in a very different place. So we think top-down control and optimization is not a solution for everything, but there are solutions based on self-organization and mechanism design. Choosing the right kinds of interactions would actually allow you to get rid of the stop-and-go traffic that I've shown you before in this empirical movie. So how to go about it? I think we are actually entering extremely exciting times for economics. There are many challenging questions out there and many new methods to go about them. And I think we should just do it in a collaborative effort across the different disciplines. Here are just a number of different areas where I think scientists should pay attention to. And it's too big for any team and for any university, so it requires a global effort. And there are other things I could mention, like price formation, coordination, considering network structures and transaction costs, social norms, and also the relevance of innovation. And certainly that cannot be summarized in 30 minutes, but if you're interested to learn more, then there are 2 books, and actually I put samples outside. Thank you very much for your interest. I'm ready for your questions.
Thank you very much, Dirk. I'm sure there are many questions and comments. Let's start with Arno Riegel.
No, it was just a clarifying question about your data categories. Did you allow in your analysis for heterogeneity? I mean, something you talked later about. I mean, you had on the one hand the selfish model and then the fairness model. So you said neither of them can explain it, but you get something in the middle. So if you allow for heterogeneity, you know some people are selfish, some people are fair, some people are more fair than others. So it seems to be pretty, I don't know, consistent with such a distribution of types of people.
This is a very fair point, and actually this is our next step in the analysis of the data, that we assume that some of them, and we'll probably be able to find out who of them behave in a rational way and who of them behaves in a fair way. So there's kind of a clash of cultures. It's difficult given the communication conditions in that experiment for them to coordinate among on one of those norms, basically, and then interactions could fail. We do actually have a paper about conflicts arising from norms if there is a variety of different norms in coexistence.
Next question, please.
I had comments about one of the last ones you showed that you did a flat line was the one about the increase in network connectivity leading to reduction. I mean, this is a well-known result in biology because when you lose the spatial structure, then you no longer have the advantage of the altruistic act because you don't have reduced things. So I just didn't like the emphasis on reducing connectivity when we apply it to banking, because what you really need, I agree with the regulation point you made, what you really need to make sure is that people get the advantage of their own good behavior by being able to form networks of people, of preferred partners. But it's not the connections themselves that are doing the damage, it's the loss.
Right. Yeah, community formation, again, would create neighborhoods that could actually promote cooperation. But today, I think many people are not aware of the situation that just networking the system more and more, as we do that with communication technology in many different areas, would create benefits in the beginning, but there could be a critical threshold where what was good in the past would be bad in the future if we continue to go on networking. So I think this is quite counterintuitive, although experts, of course, would understand the reasons for that. But I think politics and also business would not be aware of that, and that's why accidents happen. And unfortunately, they could have global scale.
Last question, Fernando.
I mean, there are many questions that let me just focus on one. I was curious about what is in the spatial presence dilemma that we discussed. What is the dynamics, the law of motion? Is it the Darwinian type of law of motion that you survival, production? I'm asking because there are, I mean, it's very well known in economics. There are many papers. For example, I can think of a paper by Samuelson, Sackett, and Myler that points to very careful analytic results that indeed spatial interaction will support cooperation under certain conditions. So this is very well known in economics. There are tens of papers written.
Absolutely. I didn't say anything else.
And this is true under a number of different specifications. For example, Darwinian dynamics, imitation dynamics. So I mean, I think it would be important to highlight.
Are you talking?
Very much about the influence of local interaction in supporting cooperation, for example, in particular, and
Okay, I'm not sure whether you refer to that slide or the one before. Okay. There's a difference between the two models, but what is important here that you would start as a Homo economicus, and after a number of generations, people would not be Homo economici anymore. They would become Homo sociali, who would not be strictly payoff optimizing anymore. They have a different character, you know. And I think it's not well understood that, in fact, the way we do business, for example, in Switzerland, in many ways is different, I believe, from the way business is done in the United States, for example. And it's not just a matter of contracts, but also the way of thinking about economic exchange is very different, I would claim.
I think this was a comment that can fill the rest of the lunch break now, certainly for discussion. I would like to thank the speakers of this morning.